So you're a bit over halfway through first year calculus, and you've just encountered the definite integral, which is most certainly one of the heroes that you'll discover in this course. You've also recently discovered this thing, and you think to yourself, what in the world is this? And then someone tries to convince you that these are actually the same thing, and you're like, but it's absolutely true. These are, in fact, the same thing. And in order to demonstrate this, we need to review a couple of concepts. We need to talk about limits, sum notation, and this thing. Our journey begins with a topic way back in the first weeks of first year calculus. We gotta talk about limits. So, what is a limit? Well, technically, the limit as x approaches a of f of x equals L implies that for all epsilon greater than 0, there exists delta greater than 0 such that the distance between x and a is less than delta implies that the distance between f of x and L is less than epsilon. Yeah, that's what I thought. Let's break it down. What is a limit? Well, it says that as the input value approaches something, the output value approaches something. And what the output value approaches is the limit. So we understand the left side of this expression to be saying, when n approaches infinity, that is, when n is allowed to increase boundlessly, what will my sum approach? And by sum, I mean everything contained to the right of this fella. Which brings us to a discussion on a notation that you may or may not be familiar with called sum notation. So what does that thing mean? Well, that thing is a Greek letter capital sigma. Sigma is a Greek equivalent of RS, so capital sigma is a Greek capital S. It means summation, hence the S. It means that we evaluate a function at a bunch of sequential integer values, then sum our results. For example, if I were to use the sigma sum notation for the function 4k squared, where k equals 1 is my lower limit and 3 is my upper limit, that would mean I substitute the integers from 1 to 3 into the function and sum my results. Wow, so cool. So the middle of this expression can be understood to mean evaluate the following product for each integer value of k, starting at k equals 1 and stopping when k equals n. What product? That product. Which is admittedly a strange product. So let's talk about it in depth. So what products are we summing? Well, we're summing products that represent areas. Areas used to estimate the area between a curve and the x-axis. Let's break it down. We are summing the areas of rectangles. The first rectangle has height f of x sub 1 and width delta x. The second rectangle has height f of x sub 2 and, again, width delta x. The third rectangle has height of f of x sub 3 and width delta x. If I add all the areas together, I approximate the area between the curve and the x-axis, and the more rectangles I have, the narrower delta x gets, and the better I can do at estimating the area between the curve and the x-axis. This, by the way, is why we need that limit. We see that as n approaches infinity, the number of rectangles goes to infinity, which means we go from an approximate area to a precise area. How satisfying. But wait, if this is a definite integral with upper and lower limits, where do those upper and lower limits fit into the formula? Let's start by breaking down delta x. How wide is delta x? Well, if I know my integral starts at a and ends at b, and there are n rectangles, I can divide b minus a into n equal spaces. That's the length of delta x. This also informs how I understand x sub k. I start at a and I go some number of delta x's to the right. For my first rectangle, I would go 1 delta x to the right. And then for my next, 2, and then 3, and then 4, and then so on and so forth. If I were to make those two substitutions, my formula would look like this monstrosity. So yeah. So if someone you know sees this expression in calculus and says, "What in the world is this?" just tell them that it's a definite integral in disguise. And if they want to know more, just have them watch the video. And make sure both of you subscribe, hit the like button, and all that good stuff.